reactions. And of course, the names of reactions, if we say, for example, the March Handbook of Organic Chemistry, see here, the March Handbook, we have a very systematic naming of reaction. Let's say oxo uncoupling, or let's say DP methane rearrangement, and so on, conversion of something to something, and so on and so on, of physical chemistry. However, a problem is that in organic chemistry we are not using such names. We are still preserving the original naming, often by the names of the chemists. For example, we have a condensation, a Claisen condensation. Of course, we can translate that name for physical chemistry name, but we are not using that in chemistry. Not yet in the handbooks. And we should know how looks Claisen condensation and hydrogen atom here. And let's say we have B. We now know in English B means base. So a base which removes a hydrogen from that position, and we have, of course, that is a reversible reaction, so we are using such the arrows here, and once more we see now the arrows which indicate here the movement of electrons. It's also a question. Does it really show a movement of electrons? It is a convention only. We know that, you know, the illustration of the atomic orbitals or molecular orbitals are lowest and highest molecular orbital occupied, highest and lowest occupied molecular orbital, so HOMO-LUMO representation, and we can now simulate that very precisely by using in silico methods. So it is something which is also very specific. It is the convention only. Why we are using that? Because it simply gives us the possibility to understand what's going on, you know, not in the very detailed way, but something that is sufficient for investigation or organic reactions. So it is also the way that we are trying to write today the mechanism, and that's a book of that. I have it here if someone is interested. The right of writing reasonable organic reaction mechanism, or in March you can also find that notation, which the name is push and pull. Push, so we are pushing everything here, you know, this arrow, this arrow, this arrow. We are related one to each other. And we are obtaining now, let's say, something like that with double bond. And let's now write here that one, the red one here, and the second molecule. So basically we'll have such a resonance structures here. I mean, we can write something like that here, and we have a minus, and we can write here the green one, and to have the product, we should write I'm writing here this resonance structures, and now we need of course a second molecule. Let's write here a second molecule. That's not okay. And of course we can write here the red one. Yes, the red one, the green, and now such a reaction which will give us simply a product. Yes, so we have here the green one. Yes, the green one. And now that's the connection between, you know, here we have a connection between, so it is this connection between these two atoms, and here we have a second one. It's very easy to make a lot of mistakes writing the chemical reactions, because even of such representation of the molecules, which will be very different, which could be presented very different. So I'm writing that all in short notation, in a compact one, not indicating all individual atoms, especially hydrogen atoms. And we have here, so here we will have the red one. Yes, the red one. Yes, and here, let's say, and here is once more, and now we have such a that's of course the replacement reaction, the substitution, and the product will be decarbonyl the product of that reaction. We can also notice, using that representation, to have this push and pull method, which is now very popular. So simply I write only a sketch on the table, a sketch on the table will be like that. And then we have, let's say, this kind, and we should have here and that reaction, and everybody will try to know that by themselves to have a better knowledge of such writing. And we should understand that it is simply a nanotechnic method for understanding what's going on here. And to explain that, to understand, I can advertise a lecture, and I'll send now the link for that lecture. A lecture which is available for third year organic chemistry course, and it will be, let's say, lecture 16, yeah, lecture 16. So I'm sending it by, I'm sending that by the chat. From our third year course, and we can understand what is the connection between such a structure with the Lewis electron pair and a real structure of a molecule calculated by the method of the theoretical chemistry. And using that calculation method in silico, we can calculate very precisely the properties of the molecules. So it is a reality, not only a model. So everything is going okay. So we had the lecture which is recorded, and I'll present that on the internet site and YouTube, and I'll send you, or I'll just put on the Moodle the special course where we will place all the information about the available materials, about the slides. If I would use the slides of the film with high quality lecture representations. So the next is what we have is the arrows. The arrows, we have many different arrows, and even till now we have already seen that we have an arrow representation which are used for drawing mesomeric structures or molecular structures within the reaction mechanism, which indicates, as here, let's say, this indicates simply the tendency for moving electrons between the atomic centers in the chemical mechanism, the reaction mechanism. So that's the first kind of arrows which we are using. Then we have, of course, this kind of arrows, which simply means chemical reaction. Chemical reaction, which means that if we have chemical compounds represented by substances, not molecules, really. We are writing here molecules, but we are thinking about the substances. So we have a possibility of obtaining some product or a product of the reaction. So two or more chemical substances are mixed in special conditions, usually in solvents or without solvents, under the influence of temperature or some other conditions to produce the yield. So here we have reagents and products here. So we have 1, 2, 3 and so on reagent, and we have 1, 2, 3 product and so on. Then the second kind of the arrows are something like that, and we know that basically in organic synthesis we are trying to use the irreversible processes because we need, or we would like to have 100%. So we would like to have a selectivity. We don't like to have such a situation like here, which this arrow represents the reversible process. So we will have the mixture of reagents and products. Everything will be in our vitro representation. So in the lab we'll have a mixture, and we don't like mixtures. We cannot sell, for example, a mixture as a drug. We need a very pure compound here, a single one. Then we'll have something like that, such an arrow. What does that mean? This means, so this is reversible, and reversible processes are between other examples are the reactions between bases and acids. We always should put such an arrow representation in that example. And of course the reactions of bases and acids are very important. We just saw in previous experiment, in previous reaction, in the Claisen concentration that the reaction starts with a base which removes a hydrogen, and we should write that kind of arrows because it's a reversible reaction. So this is of course convention. It's just convention. We should understand that. We are chemists. We should understand that. The people who are coming outside chemistry, for them it is not easy to understand that. For example, let's say a few years ago I had a lot of lectures also for the students in biology, and let's say if I wrote something like that and then I write something like that, so you know everybody thought that are completely different compounds, and something like that is completely different. Of course we should understand there are simply no hydrogens here, and it is automatically so we have an automatic understanding what is going on. People coming outside of chemistry, they don't have such a feeling. And finally we have something like that, and it is in which we'll concentrate and in that lectures, so methods in organic chemistry, introduction to organic synthesis, which means we are having analysis from the products, and it is a target molecules, and we have a reagent here, or more precisely we are trying to find syntons. We will of course define all of this term very precisely, but I would also like to say that that kind of arrow means simply retrosynthetic analysis. And to understand what's going on, let's try to use this knowledge to know one of a very well-known reaction of the aromatic electrophilic substitution. So aromatic electrophilic substitution, let's say we would like to have an aniline, so NH2 group, and we have here of course what will be the reaction. A typical reaction will be like that, so we have here a nucleophile and here we will have an electrophile. In each reaction, either we have such a situation that nucleophile is reacting with electrophile, or we have a radical representation of molecules reacting in radical reactions. But basically we concentrate, or we are focusing in the third year course or even now on such reaction, and we should once more remember that first, it is a reversible process. Second, we are not writing here, but everybody can see that everywhere here we have a hydrogens, yeah? We have 5 hydrogens more here. No one cares to write that. So we are not writing because we are advanced chemists. However, if you present that for somebody who is coming outside of chemistry, who will not understand that. It's very important. You should be a person who then, if you are working in any company, would have this possibility to explain that to the guys coming outside of chemistry, let's say the computer sciences, or the guys who are managing or trying to find products on the market, and they ask, okay, is that the same or not? Even to the worst, I can write something like that, only with a single hydrogen, because I would like to indicate some problems. And okay, we know that we have a driving effect of this nitrogen here, because it's once more the Lewis pair in that position, and that the reaction will take place in the so-called ortho position. Yeah, ortho is also not very precise name. We should say 1, 4, 1, 2, 3, 4, position 1, 4. However, very often we are using that, para position. It's of course para position. And we are writing hydrogen and electron here, but not anymore with plus, because I would take some electrons from here, yes, and a plus is located now here. And we can write now all the structures which are simply the resonance structures. So we are writing these structures here. Hydrogen, yeah, and once more a plus sign will be where? It will be here. And now we have this pair of the electrons which can form here a double bond. Of course, now we'll have a plus sign here, and next the last structure will be just from that one to that one, so it's 1 and that one is 2, so this is 1 and the second one will be 2, and we'll have something like that, and a plus sign here, and H2, and we have all the structures drawn. Of course, hydrogen here, we should put hydrogen because we'll see in a moment that such a draw without that hydrogen has completely different meaning. So basically we do not need any knowledge of the chemistry of the reactions to write something like that. We can now change the position of the attack of that electrophile, so meta and ortho, and we can deduct from the number of the structures, resonance structure, which position will be occupied in reality in lab, and we know that such a substituent will draw the reagent in the ortho or para position. But we should also remember it is a convention only. It is a convention only. We are then discussing, you know, the placement of a plus and minus sign, and we know from that lecture on organic chemistry that if we check that in reality, a real placement, a real location of the electron pairs is not completely the same as we are writing, but it is the way that mnemotechnically we can predict some properties, some reactivity of chemical substances. So we are using that.